So last week when we looked at the different common types of organometallic reactions, you probably have noticed that a lot of these reactions, whether it was a ligand substitution reaction, oxidative addition, alkyl and hydrogen migration, or beta hydrogen elimination, most of them included the presence of a carbonyl-based complex. So how do we synthesize one of them? There are pretty much two common ways to produce carbonyl-based complexes, depending on if you actually want to produce a carbonyl-based complex that is neutral or a carbonyl-based complex that has a charge, such as a negative charge like an anion. You're going to have to take a different route. So if we at first look at how we can synthesize, produce a neutral carbonyl-based complex, how do we do that? The first thing to realize is that if you do not start with a carbonyl containing complex, you're going to have to add a source of carbonyl. And it's not that simple to just say, well, I'm just going to add carbonyl, like a carbon monoxide, and hope for the best. In this case, there's a reason why it's called a reductive carbonylation, is because we actually have to use a powerful reducing agent for the reaction to actually be able, for the metal, to actually be able to get attached to a certain number of carbonyl ligands. So in this first case, when we are looking at the carbonyl that is involved here, right, the source of carbonyl is carbon monoxide. As you notice here, this molybdenum complex does not start with any carbonyl ligand. So it's actually quite a challenge practically to be able to attach. In our case, we want to attach 6 carbonyls, right, because we want the molybdenum compound here to obey the 18 electron rule. So to be able to do that, we have to use triethyl aluminum. That is a powerful reducing agent, and we also have to use high temperature and pressure. So when I say high temperature, 373 K, that's 100 degrees Celsius, and then a pressure of 200 atmosphere. So it's quite of a high pressure. So for this to be happening, right, we need the presence of the reducing agent, we need the presence of the higher temperature than room temperature, and we actually need to be performing this reaction at high pressure. Those are the only criteria that will pretty much produce a metal carbonyl complex that will obey the 18 electron rule. By the way, I just want to let you know that those reactions here are not balanced. There's actually a lot more going on at the same time. But I don't have the time to get into this, because really the purpose of me asking you questions like this is for you to be just able to predict the main product, which is going to be carbonyl based, and also to be able to do so by looking at the reaction conditions to be able to predict what's going to be formed. Okay. The other thing that can happen is that maybe you actually do want to have a carbonyl metal complex, but you don't start with the right one. What I mean by that, if you, for example, start with a carbonyl complex containing a metal center that is iron, but you do not want to form an iron carbonyl complex, you actually would rather have a tungsten-based carbonyl complex. So we can do that. That means we need a source, obviously, of tungsten, right, which is this complex here, and we can mix our tungsten complex with an already existing carbonyl base complex. We mix the two together at high temperature, and the switch will happen. We only need high temperature. We don't need a reducing agent to do that, and we also don't need pretty much a high pressure. We just need high temperature to be able to do so. So the two metal centers will get switched, and obviously we want the tungsten metal complex to obey the 18 electron rule. So we'll need to have 6 carbonyl, right, around the tungsten to obey that 18 electron rule. So both of these complexes here, as you notice, right, they both have 6 ligands, which are all carbonyl ligands, and therefore they do have an octahedral molecular geometry. Okay. So the reason why these reactions here are requiring high temperature is because we only want carbonyl. So there's no like intermediate step where you may have, for example, in this case, 4 carbonyls and a chloride. It does happen, It does happen, but here those reaction conditions are going to drive the reaction to completion for the molybdenum and here the tungsten-based complexes to obey the 18 electron rule. So this is one way, and to tell the truth, the most typical synthesis to be able to produce neutral metal carbonyl complexes. If you do not want to have a neutral metal carbonyl complex, you want to form an anion, then you have two, again, possible ways to do so. The first way here is that, again, I have already, right, this iron carbonyl complex here that has 18 electrons, and I want to form an iron carbonyl anion, right? So one of the ways to do that is by using sodium, which again, is a powerful reducing agent, as well as naphthalene. C10H8 is naphthalene. And so those two combined together are pretty much going to reduce the number of carbonyl that we have on the iron, but you will not obviously eliminate the sodium, right? So what's going to happen is that the sodium here will form a salt with the iron carbonyl. So for the iron carbonyl complex here to have 18 electrons, you actually need to have because you don't want a neutral species, right? So you can have 5 carbonyl here. The only way that this anion here is going to have 18 electrons is by having 4 carbonyls and a -2 charge. Because if you look here, iron provides 8 valence electrons, 4 carbonyls, that's 8. 8 plus 8 is 16. I need a -2 charge to be able to get to 18 electrons, right? So my anion here will have a -2 charge, which means that the counter cation will need to have a total charge of +2. But we know that sodium can only have 1 plus charge because it's in group 1. So I therefore need 2 sodium cations with a +1 charge to counterbalance the -2 charge on the iron-based carbonyl anion. Okay, so this here, right, you're starting with something neutral, you add the combination of powerful reducing agents to form an anion, but the charge on the anion will then imply how many cations you need. Okay, all right. The complex here of the iron with 4 carbonyl, which is an anion, is going to be tetrahedral. Okay. When we start with a dimer, and we've talked about dimers before, right? So when we think here about the dimer that has 2 rhenium and then obviously 10 carbonyls, and all these carbonyls are terminal, the same thing can happen. We can actually break the dimer into 2 anions, but for that we need to have, again, the presence of sodium. And I don't recommend it at all, but it happens and it can be done. Instead of using naphthalene, we can also use mercury. So the combination of sodium and mercury will pretty much be powerful enough so that we are going to be pretty much reducing the coordination number of the dimer by cutting it in half. So you're going to be producing, right, again, an anion. And the reason why you're going to be producing an anion here that will have 5 carbonyl ligands is because, again, if you are counting, right, the total number of electrons, what do you have? You have a rhenium that provides 7 valence electrons. You have 5 carbonyls, 5 times 2, that's 10. So 10 plus 7 is 17, plus the negative charge that would provide 18 electrons, right? So this anion here has 18 electrons. This anion here also has 18 electrons, okay? So when pretty much when we are looking at complexes, right, that have the same number of electrons, we say that they are isoelectronic. They have the same number of electrons, but the really need to think about this one, right, the complex here, the rhenium complex, that is an anion. So in this case, right, we only need 1 sodium to counterbalance the negative charge, but because we had a dimer, right? And we want to balance this equation, or at least try to. In this case, it's easy. We need to add a stoichiometric coefficient of 2 in front of the entire salt, right? So the 2 here applies to the sodium. It also applies to the anion. But realistically, right, the only complex that we have present here is the rhenium-based complex. So the neat thing about this is that this complex, the rhenium complex here, is trigonal bipyramidal, has 18 electrons. This complex here, which also is trigonal bipyramidal, also have 18 electrons. So those two complexes here, the iron complex and the rhenium complex, they both have 18 electrons. They are both trigonal bipyramidal, so they are isoelectronic compound. Okay, just really the most important key driver here in being able to determine what those products are is to look at the reaction conditions. So if we start with pretty much high temperature, high pressure, and we don't have sodium and naphthalene, right, we have a reductive carbonylation. If we start with a carbonyl metal complex already, and you see the sodium and the naphthalene combination, or the sodium and the mercury combination, you're going to form a carbonyl, metal carbonyl, obviously, but an anion. And the charge on the anion is directly dependent on how many extra electrons you need for this metal complex to achieve the 18 electron rule. Okay? So those reactions are easier to balance, right? Those are a little bit more challenging because there are other things that are happening at the same time there. Again, I am not expecting you to be able to balance those chemical equations, right? But I'm expecting you to be able to predict, obviously, the products, as well as tell me what the shapes are, molecular geometry, and counting the total number of electrons, right? So identifying those different reactions, being able to predict the product, how many ligands we have attached, how many electrons we have, and what the molecular geometry is pretty much what I would like you to be able to achieve to wrap up the Unit 5. Talking about wrapping up Unit 5, what I would like you to start looking at, especially for when we're going to meet on Wednesday and when we're going to see each other, well, virtually, I guess, but we'll look at different practice problems. So we will look at those 3 reactions that I already have in your packet for the Unit 5. I would like to add one more that is a little bit more challenging, but that's exactly what I would like you to be able to do. I want to be able to identify what those reactions are. I would like you to be able to predict the product. Here I'm going to draw the molecular geometry, but I'm not going to ask you to draw it. I'm just going to ask you to predict what the molecular geometry is, count the total number of electrons in the reactant and in the product, and then be able to obviously justify where the total number of electrons is coming from. Okay, so this will be kind of a practice problem to wrap up the Unit 5, and then we'll start to introduce the topic of catalysis towards this week, midweek, and the end of the week, and then we'll wrap up pretty much the semester by looking at the 2 most important types of catalytic cycles. Okay, so I will post the Unit 6 packet on Canvas definitely by Wednesday. All right, if you have any questions, you know how to find me. And if you have any questions on how we're going to be moving forward, please check your email. I'm providing some announcements via email, and you can also always ask me questions during my office hours. You have a wonderful day. I'll see you later.